Welcome to Step 2 of the TTP-Based hunting methodology, Developing Hypotheses and Abstract Analytics. In this module, we'll review the overall methodology, our learning objectives, and how this step fits into the methodology. We'll talk a bit about hypotheses. What are they, and why are they helpful in hunting? We'll dive deep into an example technique to explore the process of creating a hypothesis and improving it. We'll continue to follow this example technique throughout the course, including in this module, how to convert our hypotheses into abstract analytics. I'll ask you to think through a different example technique. Keep in mind that both of these example techniques will be reused throughout this methodology course. So take your time in thinking them through now so you'll have a solid foundation to build upon in future modules. As a reminder, the 7 steps of the hunting methodology can be visualized as a V. The method is roughly sequential from upper left down to the filter step and then back up to the hunting step on the upper right. We visualize it as a V because we visit and then revisit the same conceptual layers in the first 3 steps and in the last 3 steps, but in reverse order. We start by characterizing, researching, and defining in the first 3 steps, and then pivot through the filtering step into an implementation phase. We start with an understanding of adversarial TTPs, and then think about analytic approaches to detect those TTPs, and then determine what data we'd need to conduct that analysis. Once we start implementing, we'll roughly go in the reverse order, starting by checking our data collection and identifying any gaps, then implementing and testing our analytics. And finally, we're ready to detect the malicious activity that we started out by understanding. In this module, we're focused on the second step, developing hypotheses and abstract analytics based on knowledge of malicious activities. At the end of this course, you should have the knowledge you need to start implementing this yourself to help defend your own systems. In addition to leveraging existing analytics and data collection recommendations, you'll be prepared to create your own. At the end of this module, you should have the knowledge you need to begin developing your own hypotheses and abstract analytics based on information about TTPs. As we walk through this module, give some thought to why we're developing hypotheses and abstract analytics. One of the key points we introduce in this module, and will come up many times again in this course, is the concept of behavioral invariance. A behavioral invariant is something that an adversary has to do in order to execute the associated technique, regardless of which tool they use. We'll consistently be focusing on the behavioral invariance, and that will provide us a more robust approach to our analysis. We're also going to talk about feedback and how to refine our approach. The first idea we developed is very rarely going to be what we end up with. This entire methodology, in fact, is iterative, and so is this step. Although this methodology is applicable to any technology domain, our examples are going to focus on Windows and IP networks. So you should have some familiarity with those technologies. It'll also be useful to have some familiarity with an analysis platform like Splunk or Elk, and of course, with Attack. To do this step yourself, you'll need to have an environment for experimentation. That environment should be as representative as possible of the systems you plan to hunt in, and should enable both threat emulation and flexible and detailed instrumentation. As you might recall, adversaries must operate within the constraints of the technologies they're exploiting. As a result, the tactics, techniques, and procedures they employ are relatively few and often common across actors. They don't change very frequently and are difficult to change for the adversary. This methodology is designed to exploit those facts for the advantage of the defender. We began by developing a solid understanding of the TTPs adversaries use. Attack documents the TTPs adversaries are known to have used in open source reporting. This second step leverages that knowledge of TTPs to create hypotheses about that malicious activity. Doing this provides us a solid foundation for our research, analytic development, data collection requirements, and our implementation strategy. Let's begin by talking about hypotheses. Oxford defines a hypothesis as a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. They are unproven ideas about why something might be happening. They might turn out to be correct, like the hypothesis that disease is caused by germs, or they might turn out to be wrong, like the hypothesis that disease is caused by an imbalance of the body's humors. They might turn out to be mostly right, but need some refinement, like the hypothesis that the Earth is a sphere. Well, actually, it's an oblate spheroid. But the original hypothesis is pretty close. Not all hypotheses are created equal. A good hypothesis will be sufficiently specific to be useful, based on evidence, and falsifiable. Let's break that down a little bit. First, a hypothesis should be specific. For example, a hypothesis that someone might try to do something on your network is extremely vague and doesn't help us do our research or build an analytic or figure out what data we're going to need to test. Getting more specific will help. So, for example, someone might try to suddenly and quickly exfiltrate sensitive data off my systems to somewhere outside my network using standard IP-based protocols through my internet access point. Now, that's a lot more specific, and it gives us a lot more to go on as we do our research, analysis, and data collection. Hypotheses should also be evidence-driven. Throughout the process of creating, refining, and testing a hypothesis, you should apply as much evidence as possible. To start, we can use the evidence of existing techniques and adversary behavior as reported while we are creating a hypothesis. We can also use evidence from local experience, our research, and previous red teams to inform hypothesis creation and refinement. As we dive deeper, evidence should drive the refinement of our hypotheses to account for nuances unanticipated when we created them initially. Finally, the hypothesis should be written in a way that it can be tested using evidence. Think through what kind of evidence would support the hypothesis and, importantly, what kind of evidence would refute it. A good hypothesis will be falsifiable. For example, the hypothesis that a malicious actor will use extreme stealth to operate on my system in a way that is indistinguishable from benign usage. Now, what evidence could possibly be used to disprove that hypothesis? The definition of the hypothesis basically says there won't be any evidence if it occurs. So it's not falsifiable. So why are we putting such an emphasis on creating a hypothesis? Why not just dive into your data and start writing analytics and see what works? There are a few reasons. First, creating a hypothesis helps to clarify your thinking about what you're looking for. And that gives you a great starting point for your research, for your analytic development, and for figuring out what data you need to collect. It also allows you to reason about the behavior in a natural way without worrying about query syntax and specific data formats. This serves as a bridge between the narrative descriptions of behaviors on attack and more concrete analytics in a specific query syntax. Finally, it provides a more scientific foundation to your subsequent hunting. The research and reasoning you do while creating a hypothesis provides a deeper understanding for why the analytic exists, which kinds of behaviors it will detect, what false positives you might expect, and what it means if the alert fires. Let's walk through some examples where we start with a behavior and then create hypotheses based on evidence of that behavior. So let's start with an example that has nothing to do with cyber. Instead of thinking about defending a network, let's consider how we defend a neighborhood. In a signature or IOC-based approach, we might try to get a list of license plates, fingerprints, and other signatures associated with past burglaries, and then set up cameras to scan for anything with those signatures in our neighborhood. In an anomaly-based approach, we might use the sensors that we have, like traffic light cameras, to detect unusual traffic patterns, like a moving van leaving our neighborhood, or cars entering or exiting the neighborhood that we haven't seen before. However, to employ a TTP-based approach, we would start by studying the behaviors of burglars. So, for example, one observed behavior is that burglars implement the tactic enter homes through the technique of kicking open locked doors to steal your property. There are other techniques that burglars use to implement this same tactic of enter home, such as the break a window technique. But for now, we're going to focus on the kick open locked door technique. So, we start by developing a hypothesis around that technique. For example, we might start by hypothesizing that if the door opens, a burglar is breaking in. However, that hypothesis is too vague, and it's likely to cause many false alarms. Like every time you walk into your own house, the door will open, and that's not a burglar breaking in. So this approach is going to have low precision. It isn't even as specific as the technique that is being described. Note that the technique is to kick open locked doors. So we can improve our hypothesis by adding some specifics about the behavior itself and hypothesize that if the door opens while still locked, a burglar is breaking in. This hypothesis is more specific and less likely to cause a false alarm. Now, let's check if this hypothesis is falsifiable. Yes, it is. So if the door is locked and kicked open, but it's for some benign reason, then the hypothesis will be false. So we can imagine a scenario where emergency services like the fire department have to kick down a locked door. And it's not to steal your property, it's to put out a fire. So in that case, this hypothesis will be false. So this thought experiment about falsifiability has led us to an insight about possible false positives, and that can let us further improve our hypothesis. So we might refine it and say, if the door opens while locked, but no 911 call has been made and no fire alarm is active, then a burglar is breaking in. So now we've added some additional specificity, and that's reduced the chance of a false alarm based on this hypothesis. So we've improved our precision. Now let's shift back to the cyber domain and apply this same process. From the information in attack, we know that one of the tactics adversaries employ in cyber is persistence. And one of the techniques to gain persistence is to schedule a task using the built-in functionality of the operating system. Now in Windows, this technique capitalizes on the functionality of the task scheduler. From this information, we can define a basic hypothesis that if a task is scheduled, an adversary is establishing persistence. Now this initial hypothesis is fairly specific and it's falsifiable. However, if we investigate the behavior a little bit more, we come to realize that applications and system administrators also schedule tasks. So this first hypothesis is likely to be fairly imprecise and will probably generate a lot of false positives. So we can start to refine it by adding a clause to try to exclude that benign activity. So our next hypothesis might be that if a task is scheduled by a non-admin user, then an adversary is establishing persistence. This is getting more specific, but is still falsifiable, and it's less likely to generate false positives. Note that we've improved the precision with this refinement, but it's probably going to be at the cost of recall, since any adversary task scheduling that uses admin credentials will now be missed by this hypothesis. And this is a good example of the tension between precision and recall that we've talked about. As we've already seen with these two simple examples, hypothesis creation is usually iterative. As we've also seen in these examples, thinking about possible false alarms is one way to refine our hypotheses. And we need to remember the typical trade-off between precision and recall, even at this early stage. Considering false positives is a great thought experiment to start figuring out ways to distinguish malicious use of the technique from benign use. In these examples, we only refine the hypothesis once, but in practice, you'll likely need to refine your hypothesis many times to strike the optimal balance between precision and recall. And we're going to dive into that more deeply throughout this course with our example technique of scheduled task. Also note that all this work has just been in English, rather than some specific query syntax like Sigma or Splunk, EQL, or SQL. And that frees us up from worrying about the syntax so that we can think in our native language. We'll also have something we can share with others even if they're using a different analytic platform and associated language. In our example, we are focusing on a signal technique at a time. However, you can also group related techniques. You can also divide up a technique into sub-techniques or specific use cases to get more granular. As we define and refine our hypotheses, it's often helpful to consider why an adversary would exhibit this behavior. Knowing the why provides some context and might hint at what other behaviors would likely occur before, with, or after this behavior. This contextual information could be used to refine and improve the precision and recall of our analytic approach, or to help investigate our initial detections. Knowing the why can also help us think through how malicious behavior differs from benign use. If an adversary is scheduling tasks to help execute code remotely as they move laterally through a network, they might create a series of events in tandem, whereas a sysadmin scheduling tasks across the entire enterprise might simultaneously create tasks on all the machines from their machine. And those two use cases for different purposes might look different when those task scheduling events are connected together into a graph across time and terrain. And that different graph topology can help us distinguish benign from malicious activity. Another set of questions to consider when developing and refining your hypothesis is to think through the activities that will occur before, during, or after the core behavior that you're looking for. How is this technique invoked by an adversary? If we look at the sub-techniques for scheduled tasks on attack, we see there are 5 different sub-techniques, including 2 that are specific to Windows. And there are at least 4 different ways to invoke those 2 Windows sub-techniques. If we can find common activities across all of those invocation methods, we could focus our analysis on those and develop a more robust analytic. Once invoked, the core behavior will occur, and that behavior is likely to trigger many second-order activities throughout the operating system. For example, many actions in Windows end up triggering registry reads, DLL loads, and file opening events. Those actions can therefore be very noisy, but there might be some useful events or event sequences in those second-order effects that could help you with your detection efforts. For all of these actions, the invocation methods, the core behavior, and the second-order effects, what are the unavoidable events and which are optional? Now, this touches on a core concept of TTP-based hunting. We should seek and capitalize on those unavoidable actions associated with these behaviors to maximize the resiliency of our analytics to evasion and to help reduce data collection and processing requirements. We call these unavoidable actions behavioral invariants because they are the behaviors that don't vary based on how an adversary implements the technique. If they exist for a technique and we can detect them, this is a great place for us to focus our efforts. Now, as you refine your hypothesis, it's useful to consider a range of benign use cases for the technique. One way to explore that space is to consider how each of several prototypical users might exhibit the behavior. For example, a typical user, an administrator, and a software developer might each exhibit the behavior differently in the course of their daily activities. What types of user or activities occur in your network that might be confused with malicious behavior? What would differ between those uses and malicious activity? Can we collect additional contextual data to help distinguish malicious use from benign? Can we influence how our authorized users behave to help us distinguish them from malicious actors? And finally, if a malicious actor steals the credentials of an authorized administrator in your network, how would you differentiate their subsequent behavior from that of the admin? We mentioned before the idea of behavioral invariants. These are the activities that are fundamental to a technique, rather than actions that might vary depending on how the technique is invoked or which tool is used to execute it. Since software developers created the technologies that an attacker is trying to exploit or misuse, there are a limited number of options for the adversary. If we can base our hypothesis around these behavioral invariants, we'll be much more resilient to evasion by the adversary. If we, or an expert threat emulator, can find a way to execute the technique without confirming our hypothesis, it's likely we haven't found or sufficiently focused on those behavioral invariants. For some techniques, there might not be a single behavioral invariant or even a sequence of behavioral invariants. And in those situations, we might need to look at the sub-technique level or break the technique down into separate use cases and find behavioral invariants associated with each level of granularity. So how do we find these behavioral invariants? Well, we need to research the technique or sub-technique thoroughly. We need to understand our own system as well as the malicious actors do, so we can stay ahead of them. We can increase our understanding through open source research about how adversaries employ the technique. Read the documentation of the relevant operating system or software and APIs to learn more about what's possible. And we can get hands-on by reverse engineering the technology, debugging it, trying to execute the technique ourselves, looking through logs that are generated when that technique is executed, and getting threat emulation experts to help us explore how that technique works and what second-order effects are generated and the resulting logs. We have reviewed some good questions to ask yourself when researching a technique, like why adversaries employ it and how their usage might differ from benign use. We've talked a bit about how to research how the technique works and its second-order effects to seek those behavioral invariants. Keep in mind that you're not alone in this work. Many security researchers have investigated these techniques and published their findings and ideas, so be sure to read up on what others have done so you don't end up doing redundant work. Check for any existing analytics, mitigations, or other defensive ideas online around this behavior. Attack, CAR, Sigma, Threat Hunter's Playbook, and countless other resources are freely available and often contain excellent information and specific analytics and mitigations for these malicious behaviors. Searching those resources first can save you a lot of time and might help highlight a gap that you can focus your time on. Engaging with the community on your ideas is also a great way to improve your work. If you've discovered something new, you can share that with others. If there's a flaw in your approach, community engagement can help uncover that early and save you trouble later on. In this course, we focus on a single technique at a time for simplicity of our examples. You should consider if there are precursor, follow-on, or correlated techniques to the one you're investigating, and think about grouping them together in your analytic approach. There might be two techniques which, in isolation, each have a high false alarm rate, but if seen together, are more likely to indicate malicious activity. The converse might also be true. In both cases, grouping related techniques can help with precision and recall. In addition to techniques an adversary might use in conjunction with each other, it might also be helpful to think through the alternatives an adversary might have. If you succeed in stopping an adversary from using a given technique, what would their plan B look like to accomplish their goal? What other techniques exist within that same tactic? Finally, we've talked about seeking and focusing on the behavioral invariants associated with these techniques. This provides a more robust analytic approach. As we've discussed, in practice, you might want to consider a set of techniques together, but in this course, we'll focus on one at a time. When you choose a technique or a set of techniques to focus on, there are many things to consider, but they essentially boil down to getting good return on your investment. We advise that you focus your analytic efforts first on techniques that are not already covered, are commonly used by adversaries, and would create a big impact if successfully used in your systems. You should also seek techniques that capitalize on existing data collection, documentation, or analytics, or that you anticipate will be relatively easy to implement and not trigger too many false alarms in your systems. For example, techniques which your typical users and system administrators don't employ. You'll have to think this through for your situation and find a good balance between these characteristics to determine how to focus your efforts. For this course, we've chosen the scheduled task job technique as it is commonly used and provides good material for exploring the different aspects of this methodology. Before you dive in too deeply with your own research and hands-on experimentation, be sure to check out open source resources and capitalize on the value they provide for free. Sigma, CAR, Bazaar, EQL, and Threat Hunter Playbook are all great resources for this kind of information. In this course, we've introduced the scheduled task job technique from ATT&CK as our example technique. We'll follow this technique throughout the TTP hunting methodology in this course. Earlier, we introduced the technique with a very rudimentary hypothesis about an adversary trying to persist on a system if we see a task being scheduled by a non-admin user. So let's explore that technique a little more and try to refine our hypothesis based on the behavioral invariants of this technique. From the attack technique page, we see that there are 3 tactics which can be achieved with the help of task scheduling: execution, persistence, and privilege escalation. We immediately gain some insight based on that tactic information into the why for this technique. Essentially, there are 3 answers: remote execution, persistence, and privilege escalation. These whys start to give us insight that will prove helpful as we refine our hypothesis and try to distinguish malicious from benign usage. And we'll see that benefit later in this course. ATT&CK also gives us some great information on how this technique can be invoked. As of 2020, ATT&CK even decomposes the technique into sub-techniques, which help us organize and focus our research. We can already see there are several invocation methods, and 2 that are relevant to Windows: and scheduled task. As we continue to research this technique, we discover additional information that helps us focus our efforts to find behavioral invariants and design an analytic approach. We find that the scheduled task sub-technique can be implemented through the command line with shtasks, via an API, or through a GUI. This indicates that we'll either need to be sure to detect all 3 of those interfaces, or find a behavioral invariant to detect, which is common across all 3. Our research also uncovers what seems to be a very useful built-in event from Windows. Event code 4698 from the security event log is triggered when a task is scheduled. Perfect. We're going to need to keep that in mind as we proceed, because if event 4698 fires across all those different invocation methods, it'll be a great event to collect and use in our analysis. In addition to our research online, we can do some hands-on investigation with free tools like Procmon or WinDebug, as well as checking our event logs after executing the technique on a test machine. We'll see that the kind of insights we can get from hands-on investigation through these examples. We know we want to find behavioral invariants, and we know that the invocation of a technique is not the only action that occurs on a system. When the technique is invoked, we know to look for second-order effects. And our hands-on investigation is a great way to discover those. We can download and start Procmon, and then schedule a task in various ways and check Procmon to see the registry and file activity, along with other actions like process and thread creation that occur as a result. Now here's a filtered down set of results from Procmon after scheduling a task. Now if this is your first time using Procmon or a similar tool, be sure to read its documentation first, since your initial unfiltered results can be a little overwhelming, and you're going to want to narrow that down to just the activities of interest. We can see here that there are many registry actions being taken to create and set keys associated with the new task. This info gives us the names of the registry keys being used. We can keep that in mind in case we decide to collect registry events and need to filter them down to conserve bandwidth or storage resources. We also see some file creation and writing activity associated with writing the new job file describing the task to schedule. Similar to the registry activity, this Procmon view shows us useful additional information, like the path to the job file, and a correlation between that path and the registry key name from above. We can also run WinDebug or some other debugging tool while scheduling a task and watch as DLLs are loaded and functions are called. As we debug, we can also check the event logs to see which lines of code trigger which events. In this case, debugging shows us that XML-Lite DLL is being used to create the job file XML content, and that shtasks invokes the taskSched DLL, which is common with the API and GUI invocations, and that an RPC runtime DLL is called, which makes a syscall that executes both the registry key creation and the job file creation. And we see that both the 4663 registry event and the 4698 scheduled task events both fire during that syscall. Based on our research and some hands-on investigation, not all of which we put in this briefing, we came up with a few candidate behavioral invariants. First, we note that all of the invocations created a job file in the task directory. That seems to be a behavioral invariant so far. However, file creation activity is likely to be very noisy, so we'd need to be able to filter it down. File creation events also don't provide information about the contents of the file, so our ability to refine our analytics based on that job file content would be limited. We also note that the location of these job files could be configurable, so filtering to a specific directory, while possibly in helping improve our precision, might create a blind spot and diminish our recall. A second candidate is the registry activity we saw. Windows has a built-in event for registry changes, and we know the default key values associated with task scheduling, so we could filter those events. However, these events will have similar potential problems with the file creation events. Filtering to specific key values might create a blind spot, and the event content doesn't have enough info for the analytics refinement we might want to do later. A third candidate we found, although we didn't explore it in these slides so far, is that remote task scheduling uses the endpoint mapper port followed by an ephemeral port associated with task scheduling on the remote machine. Analyzing network traffic could help us detect this activity. The port numbers we found in the task scheduler documentation are used by other applications, though, and can be reconfigured. So we'd rather find a more robust way to detect this activity. We'll stash this idea away for later and see how future research will identify a nice alternative using Zeek. Finally, we've seen that there are some consistent and characteristic DLLs being loaded. DLL loading is a very common activity though, so those events are likely to be quite noisy. So far, no easy answer, but we have some leads and we understand their pros and cons. So we'll keep these in mind as we continue our research. We've learned a lot through researching open source and doing our own hands-on investigation. So let's summarize what we've seen so far for task scheduling on Windows. There's a main sequence of activity, which is invariant to implementation, invariant to invocation, and even invariant to use case. That sequence is that a process is created, certain DLLs are loaded, special registry keys are created and set, and a job file is written. In addition to that, if the task is being scheduled remotely, we know that a networking DLL is loaded on the source machine, and network activity will occur associated with the task scheduling service on the destination machine. And the port numbers will be based on either using the default port numbers or whatever's configured for that network. Although there are many ways to schedule a task in Windows, there are some behavioral invariants of registry modification and job file creation which we can rely on. We also know that the 4698 event is triggered during some of those actions. In addition to the research we did into how this technique is invoked and finding the behavioral invariants, including the second-order consequences, we should consider what benign use of this technique looks like so we can distinguish it from the malicious uses. You can view all the tasks currently scheduled on your machine by running shtasks at the command line with the V option, along with FO to export it to a CSV file that you can analyze. A typical Windows instance might have a couple hundred tasks scheduled for benign reasons, and those tasks might be scheduled to run as a wide variety of users, including some that have elevated privileges. So how will we distinguish the malicious scheduled tasks from these typical benign ones? Well, we could try to create a baseline of known good scheduled tasks and exclude them from all future queries. But there's a risk that every time there's a new benign scheduled task, then it won't be in the baseline and it will trigger a false alarm. And your analysts will have to investigate every new scheduled task to determine whether it should be on the baseline or not. Now you could have a rolling baseline that keeps updating itself, but maintaining that baseline is probably going to require some human review and some work. And you might end up baselining some malicious task scheduling while you're at it, which would defeat the purpose. Now we could also add some qualifications to our analytic approach to detect the task scheduling event as it occurs and look for features that indicate malicious use, like a request to run with maximum privileges or scheduling the task on a remote machine. Taking that approach will require continuous monitoring rather than just taking snapshots of the currently scheduled tasks. And that'll have a couple of benefits. We want to do that so that we can catch the activity as early as possible instead of waiting for the next snapshot to occur. And that will help us ensure that we see all of the scheduled tasks, even if an adversary, in an attempt to cover their tracks, tries to delete their own scheduled tasks later on. So we created an initial hypothesis around scheduled tasks, and we've researched the technique to understand it better and try to find the behavioral invariants. Now we should try to improve our hypotheses. In this section, we're going to discuss the process generally and then return to our example technique to see how it applies. Hypotheses can be expressed at different levels of detail, and high-level hypotheses can be decomposed into finer-grained and more specific hypotheses. For example, the TTP-Based hunt methodology is really based on a high-level hypothesis that adversaries will attempt to operate on my networks using common tactics and techniques as constrained by the underlying technologies I'm using. we can think of our approach as a hierarchy of hypotheses, starting there at that top level hypothesis and driving down to a much more specific set. So for example, at the level of an adversary's campaign, our hypothesis might be that an adversary is trying to steal my secret information. And I might decompose that to several more specific hypotheses, such as that they will use a known exfiltration technique. Or more specifically, a component hypothesis within that might be that the adversary will use a specific exfiltration technique like web service. And finally, that hypothesis might contain many others, including a sub-hypothesis that they will use the sub-technique called code repository. And each of those hypotheses is associated with an analytic that's commensurate in detail and specificity to that hypothesis. As we develop our hypotheses, we'll want to refine them iteratively to reduce false positives and create more robust analytics. In the course of thought experiments about false positives, experimentation with and research into the technique, as we've seen in the previous slides, and through purple teaming and operational implementation, we are going to find false positives and maybe some false negatives that will require refinement of our hypotheses. Based on the initial description of task scheduling behavior from attack, we develop a rudimentary initial hypothesis that if a task is scheduled, an adversary is trying to accomplish one of the three tactics associated with the technique. So this is a pretty high-level hypothesis in that hierarchy. But this hypothesis is too vague to really be useful or actionable. Now that we've researched the behavior, though, we can refine that hypothesis. One way we can do that is looking at the three primary use cases for task scheduling: local scheduling, remote scheduling, and scheduling to run as a privileged user. So for local scheduling, we can focus our analysis on the behavioral invariance of creating a job file and the associated registry keys, and we can refine our hypothesis accordingly. For remote scheduling, we need to consider the fact that there are going to be two computers involved: the source of the scheduling and the destination where the task gets scheduled. On the destination machine, we'll see the same behavioral invariance as in local scheduling. But on the source computer, we could look for different things. We could look for specific invocations of task scheduling and see when they're associated with a remote scheduling event. And that's pretty easy to do for the command line, although it might be a little more difficult if they use API or GUI. And that approach might be vulnerable to evasion by modification of the executable name. So, as we've said, this methodology is iterative, and we'll use this use case as an example of when we have a suboptimal approach, but we need to just press ahead, keep making progress, move on to future steps, but keep in mind that we're always going to keep seeking ways to improve, especially this particular approach. Now, given that approach of using the command line detection for remote scheduling, we'll need to think through how malicious use might differ from benign use to minimize false alarms. And since system administrators are likely to also remotely schedule tasks through the command line, we're going to want to filter their activity out. Our first idea might be, well, let's exclude administrator hosts from our query. And this is another example of the typical tension between precision and recall. By adding this exclusion, we will probably improve our precision by reducing the false positives that we expect to get from sysadmin activity. However, this will also probably reduce our recall by creating a big blind spot for our analysis that could be exploited by an adversary by collecting the credentials of our sysadmins and conducting remote task scheduling from their machines using their credentials. And this behavior seems plausible since an adversary is going to want to try to blend in, and acting as if they are an admin would be a great way to do that. And in fact, a search of attack shows that the use of domain credentials, including those of administrators, is a known technique used by adversaries for defense evasion. Finally, the third case for task scheduling is to run a task as a specified user. We might decompose our hypothesis to focus on those scheduled tasks which are scheduled to run as a different user from the one scheduling the task. In these refined hypotheses, we can already see the beginnings of analytics and the associated data collection requirements that those analytics will have. And our next step is to convert these hypotheses into abstract analytics. In this section, we'll define abstract analytics and use our example hypotheses to create associated abstract analytics. As you've seen, hypotheses are written in a native language, like English. This provides a freedom of expression and thinking that is helpful at the start of our process. An abstract analytic can also be written in English, but we could choose to use some kind of pseudocode instead. Once we have a solid hypothesis, converting it into an abstract analytic helps to structure our thinking a little more and more clearly describe the detailed conditions that should trigger an alert. In the example of our burglary scenario, an abstract analytic might define an object door with a state opening, and another object door bolt, which might have a state extended. And we want an alert to fire when both of those states are true. You can decide how formal you want to be at this stage. If you're very familiar with a particular syntax and feel very confident in your analytic logic, you could write this in a query syntax. But you don't need to, and keeping the syntax a little more fuzzy might be appropriate given the relative immaturity of our thinking about this analytic approach. As usual, there's a trade-off here. Now this time it's between fluidity and specificity, and you'll need to decide what's right for your situation on a case-by-case basis. Here are a couple example abstract analytics associated with our hypotheses. In the first, we've chosen to keep the syntax fluid and informal by continuing to use English, but adding specific details relative to the hypothesis itself. In the second example, we've chosen a slightly more formal syntax. Now the first example will probably be easier to modify and keeps our thinking more open to different implementation options. Whereas the second will probably help us think through the logic more clearly and will more directly facilitate the translation of this abstract analytic into a specific query on our particular analytic platform. And that second example might make it easier to share with others. Similarly, for remote task scheduling, our abstract analytic example highlights the specific conditions and even starts to suggest some data collection requirements and log field names. On the one hand, this is helpful for thinking through event codes we're going to need to collect and logging configurations. On the other hand, we might be premature in assuming how we will construct the final logic of our query. So again, there's a trade-off here. Now in this final example for step 2, we again provide two possible abstract analytics. The first remains expressed in English, and the second uses pseudocode. In the local scheduling example, we chose to use the file create event in our abstract analytic, which will lead us to collect file creation events and was based on the car data model. In that example, complying with an existing data model might aid us in converting the abstract analytic to specific data collection requirements. In this example, we've invented a custom event called task scheduled, which is not in the car data model. Now, this approach leans away from specificity and keeps our thinking more fluid to alternatives, like, for example, event code 4698. As we wrap up step 2, we have a much better understanding of the malicious behavior, including behavioral invariants, the reasons why an adversary might exhibit this behavior, and how that might look different from benign use. We use that knowledge to define, decompose, and refine hypotheses, and created abstract analytics associated with those hypotheses. In the next step, we'll develop data collection requirements driven by the hypotheses and abstract analytics developed in this step. As an iterative process, we'll also continue to refine our hypotheses and analytics as we explore available data sources and see which are triggered by the behavioral invariants and what metadata they provide to help distinguish malicious use from benign. When we're on a real network and start collecting data and ingesting it into an analytic platform, we'll be ready for step 6, where we implement these abstract analytics as concrete queries. At that stage, we'll be ready to tune and test the analytics based on the real data from our production systems and validate they work through purple teaming. Having completed step 2, we're better prepared for that future work, for communicating with others about our approach, and to interpret the results we get when we deploy these analytics and start getting hits. For context, here's where we are in the overall 7-step process. We started with a malicious activity model, and now we've developed associated hypotheses and analytics. We'll carry those through the next few steps and refine them so they're ready for implementation, testing, and tuning in step 6. And that will provide a solid foundation for the hunt.